So let's do Ohanian problem 2.18, one of the practice problems for our first homework assignment. So Ohanian says a hunter shoots an arrow at the deer running directly away from him. So we know this, first of all, is a one-dimensional problem. I'll define an x-axis with x in the positive direction. And I'm also going to go ahead and choose my origin, x equals 0, where the hunter is. I want to be the hunter and not the deer. Okay. When the arrow leaves the bow, the deer is at the distance of 40 meters. So the deer, like everything else, will represent as a particle. Its original position, x sub deer naught, is 40 meters with respect to our origin. Okay. And when the arrow strikes the deer is the final distance of x deer final, xdf, equals 50 meters away. Okay. The speed of the arrow is given. I'll just represent that with a little arrow and note that it's 65 meters per second. The problem asks what must have been the speed of the deer, v deer, and how long did the arrow take to travel to the deer. I'll call that delta t, and note the delta t for the arrow to be in the air is the same delta t as for the deer to travel from 40 to 50 meters, so I don't need a subscript for delta t. So how do I get started? Well, sometimes you want to backward engineer the problem, and I realized that I could solve for the velocity of the deer using that's equal to the delta x of the deer over delta t, and I know delta x of the deer is final position of the deer minus initial or original position of the deer, or 50 minus 40 equals 10 meters. That's all well and good, except I don't know delta t. So I'm temporarily stuck. Let's focus for a moment on the arrow. The velocity of the arrow is delta x of the arrow over delta t. Okay, and I know the velocity of the arrow, and I know delta x of the arrow. Okay, it travels from 0 to 50 meters. So actually I can use this to solve for delta t. The time the arrow's in the air is equal to, just rearranging this equation, delta t equals delta x of the arrow over the velocity of the arrow. And that's 50 meters for the arrow. 50 where it starts, it was originally at 0, divided by 65 meters per second. Pull out the calculator, which I've already done, and that's 0.77 seconds to two significant figures like the values were given, and circle that because that's one of my answers. It's actually the answer to the second question, but that's okay. You don't have to answer questions in the order they're asked. You just have to answer them. Okay. Now that we've got the delta t, we can go back up to the velocity of the deer and say the velocity of the deer is the change in position of the deer divided by delta t, which is 10 meters, divided by 0.77 seconds, or 13 meters per second. And that's the answer for the velocity of the deer. Now, I've already checked for significant figures. The dimensions or units are right, seconds and meters per second. How about the reasonableness of the answers? Well, being in the air for less than a second sounds about right for an arrow. Can a deer run at 13 meters per second? Well, unfortunately, I still don't think clearly in meters per second in SI units, so I made the conversion to miles per hour and found that was 29 miles per hour, which would be pretty fast for a human to run, but may be reasonable for a deer running away from a hunter. So I'm satisfied with my answers. Done.